Welcome to This Explainer. Today, we're diving into a seriously fascinating advancement in computational mechanics. We're going to focus specifically on a method that's radically improving deep learning predictions for short fiber reinforcement composites. It's all about how researchers are finally bridging the gap between those highly accurate but incredibly slow physical simulations and the super fast but sometimes, unreliable AI models. So let's get right into the big question we're tackling today. We all know artificial neural networks are incredibly powerful, right? But when you apply them to materials science, specifically when you're trying to model the path-dependent plastic deformations of composites, they hit a major wall. When the AI tries to analyze these complex stress and strain relationships, it frequently spits out noisy, erratic predictions, especially when the stress levels get really close to zero. The question is, can we actually eliminate that noise without having to completely tear down and retrain our models from scratch? To figure that out, we're drawing our insights directly from this brilliant paper by Petter Uvdal and Mosin Merkaloff. It was recently published in the journal Engineering Applications of Artificial Intelligence, and their research lays out a real breakthrough approach. It's built around something they call test-time data augmentation, or TTA for short. Here is our roadmap for the explainer. We're going to cover the composite challenge, RNNs and prediction noise, the baseline architecture, the TTA methodology, visualizing variance, and finally, wrap up with accuracy and speed up. Section 1. The Composite Challenge. The need for reliable modeling and short fiber reinforced composites. Short fiber reinforced composites are absolutely vital for lightweight manufacturing in the automotive and aerospace industries today. But here's the catch. Accurately modeling their nonlinear, elasto-plastic behavior under stress is just incredibly difficult. Traditionally, engineers have been stuck choosing between two extremes. On one side, you have high-fidelity, full-field models, like fast Fourier transform simulations. These are incredibly accurate, but computationally, they are agonizing. We're talking about 50 minutes to complete a single simulation. On the flip side, standard recurrent neural networks, or RNNs, offer a tempting alternative. They're blazing fast, but they suffer from data scarcity, and crucially, they just lack reliability in certain edge cases. To really understand why those physical simulations take so long, just think about these representative volume elements, or RVEs. Engineers generate these to mimic the actual physical microstructures of the materials. Notice how the fibers can be oriented in these wildly complex 3D random patterns, planar layouts, or unidirectional formats. Calculating all the physical interactions within these stochastic geometries is exactly what creates those massive computational bottlenecks. Section 2. RNNs and prediction noise, the problem with near-zero stress predictions. To bypass those 50-minute wait times, researchers naturally turn to AI. But as they train their neural networks on this micromechanical data, they ran into a massive roadblock. Take a look at the target data here, that solid black line. That's the actual micromechanical simulation target, the absolute ground truth. Now compare that to the RNN's prediction, which is the jagged pink line. You can clearly see the neural network going totally haywire. It produces a highly noisy, chaotic signal right when the shear stress component nears zero. Obviously, this kind of noise is a deal breaker if you want to use this model for real-world engineering. Section 3. The baseline architecture, modeling six-dimensional stress-strain evolutions. Before we can talk about fixing the noise, we need to objectively understand the neural network that's processing these stress paths. And they didn't just use a basic off-the-shelf network here. This is specifically designed for sequential data. This baseline architecture relies on three gated recurrent units, or GRU layers. The input layer takes in a 13-dimensional vector. That includes strain components, orientation tensor components, and fiber volume fraction. This feeds right into the three GRU layers, each packing 500 hidden states. This exact setup is crucial because it maintains memory across what they call pseudo time steps. This allows the network to model history-dependent plasticity before passing it through a 50% dropout layer to finally output the six-dimensional stress predictions. Section 4. The TTA methodology, augmenting during inference. So how on earth did we fix that near-zero noise without throwing out the whole architecture or spending weeks retraining it? Well, the authors developed a framework to augment the data during inference, meaning they do it at the exact moment the AI is being asked to make a prediction. Instead of just feeding a standard input to the RNN and crossing their fingers for a clean prediction, the input coordinate frame, so the strain orientation tensors, is randomly rotated in a three-dimensional space multiple times. The neural network then makes a separate prediction for every single one of those uniquely rotated inputs. It all breaks down into this really elegant four-step process. Step 1, randomly rotate the input tensor using Arvo's algorithm. Step 2, predict the output using the existing RNN. Step 3, take that prediction and apply an inverse rotation to snap it right back to the original configuration. And finally, Step 4, aggregate all of those back-rotated predictions into a single averaged output. By generating multiple predictions from these different spatial perspectives and averaging them out, the algorithm basically smooths out the anomalies. You're left with a robust, noise-free final stress path. Section 5. Visualizing variance, using TTA as a reliable uncertainty estimator. The cool thing here is that TTA doesn't just give us a smoother line, it essentially gives us a window into the AI's thought process. Because it's producing hundreds of varied predictions for a single input, we can actually measure the standard deviation to mathematically quantify the neural network's uncertainty. To prove how well this works, the researchers generated 100,000 back-rotated predictions for a single input. Just look at this perfect normal distribution of the mean relative error. The red dashed line on the left is the error of a single initial prediction without any rotation, which actually happened to be quite accurate in this one specific lucky case. But the blue dashed line in the center represents the average error across all 100,000 rotations. This completely proves that taking the average aggregated prediction gives you a vastly safer, more stable result across all possible configurations, rather than blindly trusting a single initial prediction. Taking it a step further, they mapped the error of those 100,000 spatial rotations onto a sphere and then flattened it out using a mall-wide projection. The colors here represent the error level. What we're seeing are actual distinct clusters of high and low errors, depending purely on the spatial rotation of the input. It beautifully visualizes the network's inherent biases and shows us exactly why generating multiple spatial perspectives and aggregating them effectively neutralizes the AI's blind spots. Section 6, Accuracy and Speed Up, Quantifying the Benefits of TTA. Okay, we've established the methodology, and we've visualized why it works. But let's talk hard numbers. Just how much better and faster is this framework in practice? Let's look at the accuracy first. The good news is, you don't actually need 100,000 rotations to get the benefits. By utilizing just 200 random rotations during inference, the TTA method successfully reduces the overall mean relative error of the predictions by a massive 19%. It effectively irons out that near-zero noise we saw earlier, which dramatically improves the shape consistency and the overall reliability of the AI's output. Second, let's talk speed. Now, you might think running 200 predictions per sample would completely bottleneck the system. Well, it doesn't. Generating an aggregated prediction using 200 rotations takes just 1.85 seconds per sample on a standard workstation GPU. When you compare that to the 50-minute traditional fast Fourier transform simulation we discussed at the start, you are looking at a staggering 1,600 times computational speedup. And you get all that while maintaining strict mathematical reliability. This research, coming out of Mohsen Mirkalaf's Mechanics and Physics of Materials group at the University of Gothenburg, is absolutely game-changing. It establishes a robust, highly efficient mathematical framework for optimizing deep learning in material science. It achieves much higher accuracy, it provides a reliable uncertainty estimator, and it does the whole shebang entirely without requiring the expensive, incredibly time-consuming process of retraining the original model. As we wrap up this explainer, I want to leave you with something to ponder regarding the broader implications here. If test-time data augmentation can so elegantly solve noise and uncertainty in recurrent neural networks for composites, how might these exact same tensor rotations revolutionize large-scale transformer models next? Could this literally be the key to eliminating uncertainty across all data-driven physics applications? It is an absolutely fascinating space to watch. Thanks so much for joining us for this deep dive.